And here we're going to look at several consequences of chain rule. In total, we're going to cover 4 consequences or applications of the chain rule. We're going to do 3 this week, and then the 4th one I'm going to push off until next week. Well, I was planning on that, but I'm still including it in this list. First, we're going to find derivatives of inverse functions. Then we're going to do a topic called implicit differentiation. Differentiation squeeze in there. Differentiation ends with T-I-A-T-I-O-N. As it is here in 3, logarithmic differentiation. And 4 is related rates, which is, I would say, by far the hardest of these 4. But I would also say among the hardest things in Calc 1. And I am going to cover that next week. But we're going to do the first 3 this week. And first, we're going to just recall the notation for the chain rule. Chain rule says the derivative of a composition, f of g of x, is f prime of g of x times g prime of x. So the derivative of f times derivative of g, where we leave the insides alone. So first, we'll do the derivative of an inverse function, derivative of f inverse of x. Right here is the notation for the derivative of the inverse. It's kind of, I wish I could think of a better way of writing this, but this does seem like the most succinct way of writing it, and it is the standard way of writing it also. So here we have f inverse prime of x. It's a function of x. And we will, I would like to get rid of the x, but we actually will need it for organizational purposes. But here we want to find f inverse prime of x. Well, we're going to just first remember the definition of a property of an inverse function. Recall, the definition of an inverse function said that f of f inverse equals f inverse of f equals x. The definition of an inverse says f of f inverse equals x. So x equals, actually I should put it on the other side as I initially was writing. F of f inverse of x equals x. The definition of an inverse function. F of f inverse equals x. F inverse of f equals x, but we'll, so that what we want shows up, we'll use this definition, f of f inverse. Well, just differentiate both sides. So differentiate, meaning take the derivative. Differentiation is the process of taking a derivative. Differentiate is the verb. So differentiate with respect to x. Frequently in math, with respect to is abbreviated WRT. Differentiate with respect to x. What do we get? Well, the left side we have a composition, so we can apply chain rule. Derivative of a composition. Derivative of the outside, leaving the inside alone, times derivative of the inside. Derivative of the outside is f prime of the inside of f inverse of x times the derivative of the inside. What's the derivative of the inside? Well, the inside is f inverse, so the derivative of the inside is the derivative of f inverse. So we have the derivative of the inside. Right here, the inside is f inverse, so the derivative of the inside is the derivative of f inverse. Equals on the left side, or on the right side, equals 1. I'm actually going to write up here because I don't think I'll be able to fit it down there. Remember, our goal was to find what I just erased. F inverse prime. Well, look at that. There's f inverse prime. How do you solve this equation for x? You get rid of the 2. How do you solve this equation for what is double underlined? You get rid of what's underlined. So I'll say, so f inverse prime of x, which is double underlined, equals 1 over that thing. F prime of f inverse of x. This is a nice consequence of chain rule. even if the notation is a little unpleasant. And this is the derivative evaluated at the inverse. That's a little unpleasant. This is the derivative of the inverse. A little less unpleasant, I would say, than that. But all we did was take the relation that the inverse defines, well, the relation that defines the inverse, I should say, and apply the chain rule, and then solve an equation like that for x. Next, we'll talk about topic 2, implicit differentiation. And we'll start by recalling a circle is not a function, meaning y is not a function of x for this curve. Why is that? Because of the vertical line test. That's not a function. And because of that, we can't explicitly define y in terms of x, meaning we can't say this function is y equals something with a bunch of x's. We can, however, describe that curve using an equation with x and y. And we say y is defined implicitly in terms of x, since x and y satisfy this equation, x squared plus y squared equals 25. Notice, if you try to solve that for y, you're going to have to make a choice, and that choice causes the vertical line test to fail, because you'll get y equals what? Plus or minus 25 minus x squared, which is not a function. But we can say y is implicitly defined in terms of x. And when we have an equation where y is not explicitly defined in terms of x, but implicitly defined in terms of x, we can use the chain rule to find the derivative of y with respect to x. So here in this example, find dy dx, and we'll see where the chain rule shows up. X squared plus y squared is 25. Again, we want the derivative of y with respect to x. So we're going to differentiate with respect to x. And what do we get? I'm going to go down, I guess. No, I'm going to go, I'll go over. Differentiate with respect to x. Well, the derivative of x squared with respect to x, that's still 2x. What about the derivative of y squared with respect to x? Well, y is sort of defined in terms of x. So we can think of this y squared, I'll say, I don't know, sort of equal to a bunch of x's. Bunch of x's, potentially. Squared. How do we take the derivative of a bunch of x's squared? Well, we use the chain rule. Derivative of something squared is 2 of that thing. But then you need to multiply by the derivative of that thing. So what do we have? Derivative of y squared, it's something squared, so we have 2y, but then we need to use the chain rule. And the derivative of the inside, this inside is just y. I mean, it's a bunch of, y is implicitly a bunch of x's, so we can apply the chain rule, or so y is implicitly a bunch of x's, so we can take the derivative with respect to x. But when using the chain rule, this inside is just a y, so the derivative would be 2, y the first, times the derivative of that inside, dy dx. Derivative of 25 is 0. 25 does not change as x changes. So we took the derivative with respect to x, and look at that. We wanted a dy dx, and we have one. So all we have to do now is solve for it. Subtract this. Subtract that, divide by 2. It's much easier to divide by 2 when you're at a board with an eraser. Divide by y. I guess I can leave the 2's there. Divide by 2y. And you get dy dx is negative x over y. And we're okay with having this y in this answer because we can't explicitly define y in terms of x. Here we use the dy dx notation. It's very common for Calc 1 students to prefer a different notation here because dy dx requires a lot of writing. When I took Calc 1, I preferred the other notations. I'll just say, well, first I'll box the answer so you're sure what the answer is. So I'll just say here, alternate notation. We would have 2x. Instead of dy dx, you could use the y prime notation, and then solve for y prime. What do we want to do with this? Tangent lines? Yes. But before we use tangent lines, yeah, let's do tangent lines. Example. Find equations for all lines tangent. Where did I put the eraser? Find equations for all lines tangent to the curve. Notice it's not a function because we can't solve explicitly for y. Find equations for all lines tangent to the curve when x equals 3. Well, again, oh, and then solve for y prime and what I just erased. And you get y prime is negative x over y. I guess I'll leave the derivative over here since we need it. Find equations for all lines tangent to the curve. Well, we need point and slope again. Point and slope. Well, we have our point, x equals 3. Erase that. I'll just remember that. We have our point x at, well, we need the y value. So let's find y. So find y value when x equals 3. Well, substitute x equals 3. Don't write the wrong symbol. 9 plus, my head might have been in the way. I wrote an equal sign instead of a plus. 9 plus y squared equals 25. Solve for y. What do you get? Y squared is 16. What do you get for y? Y is plus or minus 4. Well, that's okay. We don't have a function, so we could use both of them. But what does that mean we have here? We're going to have two tangent lines. One at the point 3, 4, and a second at the point, still x equals 3, but y would equal negative 4 in the second point. And there would be a second slope as well. I mean, we knew it was a circle, so we knew that was going to happen. But you could see that algebraically as well. So we have two tangent lines. I was supposed to put an S up there after value, after I found the two values. That's why I left a gap there. So we have two tangent lines, so we need to find two slopes. Well, recall dy dx, we found in the previous example, is what? Negative x over y. Well, negative x over y, there's x, there's y. So negative 3 over 4. And over here, dy dx is negative x over y, which equals negative 3 over negative 4, which equals positive 3/4. Well, now we just need to write these as lines. Y minus negative 4 equals slope x minus 3. Y minus 4 equals slope x minus 3. So we have two tangent lines. Let's do another implicit differentiation. Let's do two more, actually. And in this one with the circle, finding the point was a pretty simple equation. In these next ones, we'll have more complicated equations. I won't ask you for slopes of tangent lines for complicated equations with implicit differentiation, because solving for the y value can be very unpleasant, if not undoable. Oh, I should say solving for the y values. So let's do 2 more. And the directions will be find dy dx. For the equation, where do I want to write this? Up here. 4x to the 5th plus tangent of y equals y squared plus 3. Find dy dx. Well, if you could solve for y, that'd be nice. Here you can't. Because if you could solve for y, you can take the derivative using the chain rule and the formulas. But we can't. So we just differentiate implicitly. So we differentiate with respect to x. We get 20x to the 4th here. What do we get for tangent? Well, how do we do the derivative of... How do we do the derivative of tangent of, I don't know, 7x plus 4x squared? Well, we say this is tangent of something. So we do secant squared of something. And then we multiply by the derivative of that something. Same thing here. The y can be thought of as having a bunch of x's. Derivative of tangent of y would then be secant squared of y. But you need to use the chain rule. And we're differentiating with respect to x, so we get dy dx. Well, that's the left side. What's the right side? Well, we have a y squared. What is the derivative of a y squared? Well, again, y is thought of as having a bunch of x's. The derivative of y squared would then be 2y dy dx by chain rule. Plus 0, derivative of 3 is 0. Well, before... No, not before. After we're done, I'll say what I was about to say before. What did we want to do? We wanted to find dy dx. Well, look at that. There's a dy dx, and there's a dy dx. How do you solve this equation for x? Not this equation. How do you solve this one for x? Well, you'd move that over, divide by 20, and take a 4th root. How do you solve this equation for x? Well, you put things with x together. Then you get rid of the number. Same thing. We want to solve for dy dx. Put things with dy dx together. So let's do that. This thing has a dy dx, that thing has a dy dx. So let's move this to the other side. This thing doesn't have a dy dx, let's leave it on this side. So we get 20x to the 4 equals 2y dy dx minus secant squared of y dy dx. Well, we want to solve for dy dx, so we're going to want to get rid of this 2y and this negative secant squared of y. But before we do that, we notice both things on that side now have a dy dx. So what can we do with that? We can factor it out. And once that's factored out, all we have to do is divide by that thing. So dy dx equals what? 20x to the 4 over 2y minus secant squared of y. And let's do one more. But before doing one more, let's just observe one observation. When going through this process a dy dx will occur every time you're taking the derivative of something with y. So here we have something with y, or here we have something with y. When we took the derivative, the dy dx shows up. Here, something with y, take the derivative, something with dy, or a dy dx shows up. Let's do one more of these. Let's throw, well, let's not say what we're going to throw. This one. Y cubed yeah, okay, I'll do a sine. I'll do a cosine. I have written a cosine. I was thinking we did a bunch of cosines this week, but I guess that's okay. Y cubed cosine of x equals e to the y plus secant of x. No, cosecant of x. Why not? Well, again, we're going to take the derivative with respect to x. Y is defined implicitly in terms of x, but notice in this first term what we have. Two things multiplied together. This y could be full of x's. So we have something cubed times cosine of x. To take the derivative here, we need a product rule. I'm going to do this one backwards. Derivative of cosine is negative sine. So leave y cubed alone, and we get negative sine. Plus, leave cosine alone, which we'll do in a moment, but we need the derivative of y cubed. Well, 3y squared dy dx. We're differentiating with respect to x. And then cosine of x. So what do we have here? We have a product. Derivative of cosine is negative sine. Derivative of y cubed with respect to x, 3y squared dy dx. And then you leave y cubed alone and you leave cosine alone for the product rule. How about the other side? Well, e to the y, derivative is itself, and you apply chain rule. Cosecant x, derivative is negative cosecant x, cotangent x. No y's, so you don't have to worry about that. Well, now look what we have. Let's use some underlines. That has no dy dx. We want to solve for dy dx. That has no dy dx. Notice I underline the negatives. This has a dy dx. This has a dy dx. So what we need to do is put things with dy dx together, put things without dy dx together, and then factor and solve. So let's do that. I'm going to move, I don't know, I guess I'll move this to that side, and I'll move this to that side. This is probably the first time in my life I actually did an arrow like that for these. I'm thinking that might be a good idea for the future. So move that to this side, we get dy dx. I'm going to move that and factor at the same time. Maybe I should write a little more clearly. 3y squared cosine x minus e to the y. That's not a y. Equals y cubed sine x negative cosecant x cotangent x. So bring this to the other side, that becomes a positive. Bring that to this side, you have this thing minus e to the y dy dx. Factor out a dy dx from this. You have 3y squared cosine. Factor out a dy dx from that. you're left with a negative e to the y since it's on this side. And now all you have to do, divide by this. So dy dx equals y cubed sine x minus cosecant x cotangent x all over 3y squared cosine x minus e to the y. So when you have a product rule, you still need to observe you have a product rule, but a dy dx shows up only when you take the derivative of a y. Here, we left that y alone, so we didn't have a dy dx, but here, we took the derivative of that y. So we have a dy dx here, we took the derivative of that thing with y. So we have a dy dx. Next, we're going to talk about how we can use logarithms to help us take more derivatives. Logarithmic differentiation takes two forms. We'll start with this one and then talk about the second one. But first, I'd like you to recall some of the things we already know. The derivative of x to the n we can find using the power rule. The derivative of b to the x we can find using the exponential rule. So notice in this first one, x is in the base and n is in the exponent. X is the base, the exponent is a number. The second one, x is in the exponent, but the base is a number. Well, what happens if you have an x in the base and an x in the exponent? Well, we don't have a general formula for that we can add to our list. Because x's with base and x's in the exponent don't satisfy a convenient general formula. But what we can do is introduce a logarithm. So we introduce a logarithm to help, I'll just say for now. We introduce a logarithm to help us find that. So let's do that. Example. We'll do two examples, one with x to the x and one with like a bunch of x's to a bunch of x's or something. Example. Find dy dx. Y equals x to the x. Well, what we're going to do is introduce a logarithm, because I said that would help. Now, why does that help? Well, look what happens if we introduce a logarithm on the left side. Let's look what happens in a spot where I won't have to break because of the board. Yes, that's the right side, not the left side. Well, if we put a logarithm, a natural logarithm, you could use any logarithm, but we're going to take derivatives, and the derivative of the regular logarithm, the natural logarithm, is easier to deal with because you don't have all those extra numbers floating around. So we'll use a natural logarithm. But what does this equal using a logarithm rule? Well, remember, exponents come out in front. So this x goes out front. And now, instead of having x's in a base and x's in an exponent, we have a product. And we know how to take derivatives of products. We actually know exactly how to do this one because we did it already. But we changed our original function, so we can't just say that this is still y. If you take a logarithm on that side, you're going to have to take a logarithm on this side. So let's now differentiate this entire equation, well, this equals that side, with respect to x. And I'm going to just erase this middle thing. And just say this equals x log x by the logarithm rules. What happens when we differentiate that with respect to x? Well, on the right side, I'm going to write it up here, actually. On the right side, what do we get? A product rule. Derivative of x is 1. Derivative of x is 1. Derivative of log x is 1 over x. I guess I'll leave that like that. What do we got on the right side? Well, right here we have an equation relating y and x, but y is not explicitly written in terms of x in this equation. So if we're differentiating this equation, we're going to have to use the chain rule on the left side. So we get 1 over y, and then dy dx. Because this is, in this line, y is implicitly defined in terms of x, even though it could be explicitly defined. We are using the equation where it's implicitly defined and then differentiating. So on the left side, we get 1 over y dy dx. On the right side, we get 1 log x plus x times 1 over x, which is just 1, because x divided by x is 1. And now what do we need to do? Find dy dx. There's dy dx. So we need to solve for dy dx. Well, all we need to do is get rid of that y. So multiply both sides by y. The left side is just dy dx, the right side is that. And now we can get rid of this y because we could solve for y. In the implicit differentiation examples, we couldn't get rid of the y because it wasn't explicitly defined in terms of y. But here we can, so we should. Y is x to the x, log x plus 1. So we threw a logarithm on our equation, which turned the exponent into a product, and then we differentiated. Let's do one more. And I'm going to do it over here. When I wrote these notes, I must have really enjoyed cosine. So find dy dx for this equation. Y equals cosine x to the x cubed. Now, we can't conveniently, in any way, use that first formula and substitutions to help us, because we would need 2 substitutions. But what we can do is follow the same process. Throw a logarithm on everything. Throw a logarithm on everything correctly. So log of the left side is log y, log of the right side is log of cosine to the x squared. Bring the x squared out front so that it's a product now. Well, now what do we do? Differentiate with respect to x. In your work, you don't have to write on the side differentiate with respect to x, but I do. On this side, what do we get? Well, again, we get 1 over y dy dx. What do we got on that side? Well, we have a product rule. Derivative of x squared is 2x. What's derivative of log of cosine x? I'm going to do that over here. Derivative of log of cosine x is what? Well, u equals cosine x. So you have log of u. Derivative of log of u is 1 over u. Derivative of cosine x is negative sine of x. So we have dy du. Side work, so we can redefine y as something. So we have dy du, du dx. U equaled cosine x, so we get negative sine of x over cosine of x. And you could leave it like that, but I'm not going to. Because sine over cosine is tangent. So negative sine over cosine is negative tangent. And notice I'm changing this positive to a negative, which is much more difficult for you to do in your notes. Sorry about that. So what did we do? Product rule. Derivative of x squared is 2x. Derivative of log of cosine x is 1 over cosine x times negative sine x, which is negative tangent x. Well, now we just solve for dy dx. So dy dx equals y times that whole thing. I'm just going to substitute for y right now. So cosine of x to the x squared times 2x log cosine x. In this one, you don't need parentheses on that cosine x. So multiply by y. So here's y times this right side. 2x log cosine x minus x squared tangent x. We'll put a box around that if you want. So the first form of logarithmic differentiation allows us to handle things with x's in the base and x's in the exponent. The second example I'm not going to do on the board, but I am going to post it. It'll be 1 page. It'll look a lot like this page. But what we're going to do, I guess I'll just tell you now, is consider a fraction like that, where we have a bunch of things multiplied together with exponents and x's all over. And what we're going to do is this way. Throw a logarithm on that, which allows us to split it into something that we can take the derivative, or on which we can take the derivative of each piece. And we're going to remember derivative of log of something is this way. 1 over that thing times thing prime, which is just thing prime over thing. So I'm going to post this page. And when you're teaching a class, you always hesitate to say what I'm going to say, but I'll say it anyway. I'm not going to ask this on the test. I've never asked this on a test because of how much writing, this bottom half of the page is the entire answer, how much writing it takes and how comparatively little important math is in there. But I will post it. I would like you to look through it because splitting logarithms like that is very important. They're splitting things like this with a logarithm is very important. And it allows you to understand the properties better each time you do it. So please look at this. I'll call it a logarithmic differentiation type 2 example. Type 1 is with x's in the base and exponent. So hopefully I will see you on Thursday at our workshop. If you have any questions before then, please email me.